to everybody. My name is Alessandro Paganelli, and I'm a third-year PhD student under the supervision of Professor Maurizio Casoni. And this talk, whose title is Security Issues and Performance Analysis of Future Public Safety System, aims at describing the main research results that we have obtained during these 3 years. Here, I present you a brief outline of this talk, which is divided into several parts. The first one will be about providing a description of the main outcomes regarding a research activity related to possible future system architecture for novel emergency networks. Then I will move on to describe the most important security issues that we have found in our research activity regarding the overall security issues and problems that can be found in new generation emergency networks. And then I will move on to provide you with some numerical results regarding the quality of service that multimedia service can experience from future-proof, let's say, emergency networks. Then I will move on to describe a new software tool that we have developed for objective quality of experience evaluation in the NS3 environment. As for the first part of my talk, first of all, I would like to introduce you to emergency networks. And in short, an emergency network is the communication infrastructure of any public safety system and can be used by first responders, the personnel involved directly in the emergency response, to communicate with the command and control centers that are the Emergency Operation Control Center, named as EOC, and its mobile and local version that is typically deployed on vehicles and on mobile structures that are deployed close to the emergency field. From the SafeCom program document, it is possible to summarize some of the most important design requirements for a modern emergency network. Some of them are, for instance, it should be reliable, available, and robust, of course. It should be scalable and interoperable, and it should support many different services, which can be translated into a practical QS requirements, since the overall network should be an integrated one. Here, I would like to introduce you to the eSponder project, that is a large-scale integration project co-funded by the European Union, whose goal is to study, design, and possibly implement future-proof emergency response system by using the most important ICT technologies that are currently available, as well as those that will be available in the next future. Here is where we have conducted our research activity, and in our vision, the eSponder's emergency network should adopt standard and widespread technologies, both wireless and wired, in order to make, first of all, the whole system interoperable, since this way it will be possible to make it very effective, the overall emergency response, and moreover to take advantage of the economies of scale. One of the most important outcomes of this research has been the adoption of IP as the main internet working protocol, and as the only one, actually, since it can be considered as the glue that can be used across different network technologies, and as the main, let's say, transport protocol for all the information that we like to transmit over the network. Another very important aspect is to adopt IP-friendly technologies and open technologies that can be adopted without having barriers between the various networks, such as 802.11, 802.16, and the like. Here I've reported a brief sketch of one of the architecture that we have proposed, and you can see the sketch on the right. As you can see, the overall network is a hierarchical one. It's composed of 2 layers. The first one is responsible for providing communication support and communication capabilities for the MIOC to the EOC. And the second one is responsible for providing local connectivity from the MIOC to the first responder team. As for the topologies, the first layer is sort of a mesh-based topology for the networking point of view, from the networking point of view, while the second one is a quasi-star topology, since we can find this node that we have called special node that acts as a mobile hub for the first responder team, thus providing local connectivity to them. As for the technologies that can be used for this implementation, we have found, first of all, DVB technologies, that is satellite technology for the main backhaul link and main backhaul links for the first layer, and WiMAX for terrestrial inter-MEOC links, as well as 802.11 Wi-Fi for local connectivity among the first responders of a given team, and again WiMAX for the main backhaul between the special node and the MEOC. In this architecture, the special node is a generic node of the network. However, we expect that this topological node can be actually implemented on the first responder unit carried on by the first responder commander. So he, with his movement and his movement across, together with the first responders on the field, can provide local communication and local coverage while maintaining a direct link through the MEOC. Even though this topology provides us with some important benefit, for instance, it provides us with simple QoS management and access control and AAA procedures, it provides also with a drawback regarding the special node that can be a single point of failure. However, the overall approach can be extended quite easily to introduce other redundant technologies, for instance, as backup for these links, and can be used again to implement other special nodes that can be deployed as a semi-fixed node deployed on the field to avoid the presence of a single point of failure. So we expect that this is a very flexible wireless mesh network that can be effectively used to provide communication support to first responder of the futures. Let me move on now to briefly describe some of the security issues that we have found in our research activity about security for emergency networks. These are the most important security properties that can be found in a traditional computer network, and we have analyzed them from the point of view of a novel and a new generation emergency network. And at a glance, the result that we have obtained from this research activity has been to identify what are the most important properties among these that affect by most the design of a new emergency network architecture. These are authentication, data confidentiality, and availability, as you can see in the next few slides. As for authentication, the requirements in an emergency network scenario are, first of all, this procedure should be quick and simple. It should be viable even in case of network disconnection, and in the worst case, it should be used even if only two systems that need to talk together are present and deployed. Our proposal is either to adopt identity-based cryptography, which is asymmetric cryptographic solution that uses publicly available information as a public key. And it requires a certification authority that is a trusted third party only at the very beginning of the setup of the system. So it is completely usable even in case of network disconnection, or web of trust-like models such as PGP1, where each one trusts other users by means of digital signature, let's say. As for data confidentiality and secrecy, this property can be easily implemented by means of cryptographic techniques, but the actual solution for a real implementation depends on several constraints. First of all, we need to know the various transmission standards that are adopted for possible implementation, since most of the modern transmission standards already provide these kind of capabilities. Moreover, the scope required for confidentiality, let's say from the first responder to the MIOC or from the first responder directly to the IOC, we have different requirements, of course. Moreover, additional requirements, such as the presence of QS policies and the need to enforce QS, puts other additional constraints on the design. Our proposal is either to adopt cryptography at data link layer, which actually provides us with per-hop cryptographic per-hop confidentiality, let's say, because each technology provides its own solution. So it is also possible to have end-to-end confidentiality by having a cascade of different cryptographic solutions. On the other hand, it is possible to use the combination of IPv6 and IPsec to exploit the IPsec functionalities for cryptography, authentication, and other security capabilities, and the capabilities provided by the IPv6 header that, by means of traffic class and traffic label fields, provide us with a large flexibility to perform quality of service enforcement. So these are two possible approaches to implement confidentiality and secrecy in modern emergency networks. As for availability, this in short can be implemented by adopting redundant solutions, and our proposal has been to implement replicas and caching as for computer system, while implementing redundant links and redundant technologies for the telecommunication part. However, again, this is another property, another security property that affects by most the overall design, since open issues arise when we introduce, in particular, telecommunication redundancy, since by introducing alternative technologies, we can find actually different logical networks. So, for instance, path selection among different logical networks is a new problem that come out when I introduce redundant links. Authentication issues among different networks may be introduced as well, and the like. Moreover, access control and traffic shaping issues are of paramount importance, since we have different points of access to the network. So instead of having just a single node as the special node before, we may have different points of access to the network, and access control and traffic shaping issues may come out as well. Let me move on now to describe the third part of my talk, which regards the quality of service that multimedia application can experience in this kind of emergency networks. Here, in this research activity, our goal has been to determine if the proposed architecture was good, was sufficient to provide quality of service to the set of multimedia application that we expect to have in a real deployment. In particular, some of the main questions that arose at the beginning of this activity were: can the application experience adequate quality of service? Is the proposed architecture scalable enough? Moreover, regarding different real-time services such as VoIP and video over IP, which codecs can be actually adopted? A very preliminary question about this research activity was how to determine these answers. First of all, we had to find out a possible assessment approach, which required it to be quick, flexible, and of low cost. We adopted numerical simulation because we thought that this is one of the best solutions to tackle the problem because of its accuracy, its flexibility, and of low cost. And to provide something new with respect to what has been done previously and in the literature, we adopted NS3, which is the next release of the widespread NS2 simulator, as the main evaluation tool. Here I've reported at a glance some numerical results that we have obtained during this activity. These are just mean values together with their uncertainties when available. And these are the main simulation settings that we have adopted for different scenarios, namely an indoor, a first responder network in an indoor environment based on 802.11g standard, the same network in an outdoor environment with different channel setups, actually. The chip-to-MIUC link and the MIUC-to-UC link. To provide a better understanding of these results, here, as an example, I've provided two cumulative distribution functions that we have computed by means of our simulation software regarding the VoIP service delay for, on the left, an indoor scenario, and on the right for an outdoor one. As you can see, these two curves are very similar. And in both cases, we can see that there is a very high probability that the overall delay is bounded to about 15 to 17 milliseconds, which is completely acceptable for the link we have considered for this implementation. We have repeated this kind of analysis on each link to determine under typical traffic condition if the link was good to support this kind of service. Let me move on now to briefly describe the last part of my research activity, and in my opinion, one of the most interesting one, that was focused to the design of a new software tool that can be used to perform quality of experience evaluation in the NS3 environment. The main motivation was that at the very beginning of this activity, no tool was available for NS3 to perform objective quality of experience evaluation. That is, user-perceived quality, not just, as before, quality determined by network-oriented metrics such as delay, jitter, and so on. So here, our goal was to determine what the user perceives and what was his grade of experience. So our goal has been to develop an open source module for NS3 usable for testing audio and video communication from the end user perspective. Our requirements that we considered for this design was to adopt an open source approach that allows us to share knowledge among partners within the NS3 community. Moreover, it has to be modular and OP-based and extensible with respect to application, codecs, and QA metrics. Our current release provides these features. That is, it can be used to perform video and audio assessment, even though audio assessment are only partially supported. As for the codec parts, we support H.264 for the video and G711 and G726 for audio. While for regarding the metrics that we have implemented, we have peak signal to noise ratio and structural similarity for video, while perceptual speech quality evaluation for audio, which has been implemented by means of external tool, while the previous ones have been implemented from scratch. So here I provide you with a brief sketch of the overall architecture of our tool, which starts from, in this case, it is usable for video assessments. It starts from a raw video that is sent to a codec that produces a coded video. Then we move to a packetizer that implements the actual real-time transmission protocol packetization rules that are specific for each codec that is supported by IETF. Then these packets are sent to the real sender, the software tool that actually sends and injects these packets to the network, and the receiver then performs the opposite operation and sends all the packet it receives to a multimedia file builder for the final build. Then, by means of a decoder, we can obtain a raw video at the reception side that can be compared with the previous one, in this case, with metrics such as PSNR and SSIM. By using proper software tools and proper software design approach, we implemented diverse common interfaces for multimedia content handling, that is for codecs. So we have a software wrapper that can be used to interface with different codecs and for different multimedia formats. So in order to add another codec and another format, it is, the interface remains the same, meaning that its extensible feature is very well supported. Moreover, by means of packetizers, we can implement different RTP packetization rules according to the codec we choose. To provide a brief reference numerical results, here I simply depicted a very simple network where we vary the packet loss rate of the link between the two nodes, and our goal here was to determine how well our tool was able to follow, to track the packet loss rate of the link by means of objective quality evaluation at the receiver side. Here, as you can see, this is the first case we have considered where the packet error rate of the link was 0.001. And as you can see, there are several loss events actually. But the overall PSNR and SSIM metrics are always quite satisfactory actually. And of course, by looking at the received video, it was possible to appreciate a very sufficient quality of the received one. By increasing the packet error rate of the link, it is possible to appreciate a very high drop in performance, since both metrics fall down below the previous values, and for instance PSNR is often lower than 20 and SSIM around 0.7 and as low as 0.3, meaning that the overall quality has been decreased a lot. So this kind of track was measured and was confirmed by our experiments. Here we implemented another reference scenario that was used to determine, as an example, the variation of performance perceived by the end user in case of cross-traffic. So again, as before, we have a video sender and a video receiver. We have a bottleneck link in the middle, and a cross-traffic sender and a cross-traffic receiver. The cross-traffic is a spot source, so we expect that the bottleneck is filled with the traffic coming from the cross-traffic sender, and we should expect a performance drop while the cross-traffic is present on the network, as can be confirmed by this, this performance picture where PSNR and SSIM are depicted, and between these two frame numbers, the cross-traffic has been injected in the network, and as you can see, the overall performance drop is quite appreciable. The last part of this activity was about the validation of our tool, which is very important to verify the effectiveness of the proposed development. And we used Evalvid, another widespread tool for the NS2 platform, as a reference validation process. Two assessments have been performed. The first one was the comparison of the implementation of the video metrics, so to understand if our implementation of PSNR and SSIM was comparable of that of the implementation of Evalvid, and the comparison of the dispersion of each metric around its median value by means of box plots. Briefly, here you can find on the left the two traces of the same, the value of SSIM versus frame number for the two implementation. In the red, you can see the Evalvid outcome. In the black track was our implementation. But since are quite overlapped, it is better to look at this result that provides the percentage of the error between the two curves. And as you can see, the maximum error is of about 2%, which is quite good for our implementation, meaning that practically these two curves are practically equivalent. As for the last part, here I've reported the comparison we have made between the dispersion of our implementation on the right, in this case for PSNR, and the Evalvid implementation. Even though there are several outliers, this case is for PSNR, while this one is for SSIM, both median value are quite close, and the overall dispersion is consistent in both cases, meaning that our implementation has been confirmed by Evalvid. In conclusion, interoperable network architecture have been presented and analyzed during this research activity, and security issues and security properties have been discussed as well to determine which are the most important during the design phase. Then we have performed the QS assessments to determine if the proposed network architectures and the proposed decision, the proposed implementation decision were sufficient or were good for possible deployment, and then we have developed a new software that can be used to perform quality of experience evaluation from the end user perspective. Moreover, in the end, its outcomes have been validated by means of another tool, and this proved the validity of our implementation. With this, I've concluded. So these are my publications. If there are any questions, please ask. Thank you.
Thank you very much for your talk. Questions? Okay, as far as security is concerned, the main contribution refers to the philosophy to be adopted.
Yeah, well, the first part was just to analyze how we could translate the best practice that can be found in traditional computer networks to an emergency one. Then, by introducing the constraints that we have for an emergency network based on, for instance, quality of experience, quality of service, as well as to have an enhanced security level with respect to traditional computer networks, we have modified and we have analyzed in details what the traditional issues and the traditional solution could be adopted in an emergency network point of view.
Once again, like in Calarco's work, maybe the most interesting contribution is the development of tools for realistically assessing performance in a complicated network.
Yeah, in my opinion, this has been, first of all, one of the most interesting parts of the whole work, and it is, of course, in my opinion, very important to provide users with open tools and useful tools that can be used to perform objective evaluation.
I agree with you. Research should be open and material should be accessible to the community.
As I've said before, this tool is already available, so everyone can download it and can be used. So.
Oh, thanks again. Thank you very much. So we have another talk on a different topic. And this will be given by Mr. Davide Saguatti.